Hi, welcome back everybody. Today we're going to move into Chapter 8 and specifically Section 8.1. So we're going to get away from using integrals to find areas and volumes. We're going to go way back to a topic we did in Chapter 2, and that's finding limits. 8.1 is about a rule called L'Hopital's rule, which is a very simple yet extremely powerful method in order to calculate some limits that we had trouble with back in Chapter 2. To start the video, I want to begin with a limit problem that I accidentally assigned to you guys. If you remember way back in Chapter 2, I wasn't letting you use your calculators for anything, and we ran into, or I assigned a homework problem that was finding the limit as x approaches 0 of sine of 2x over x. And our technique really that we've usually done is we've started by trying to sub in this value to see what we get. And in this problem, you end up with sine of 0, which is 0 over 0. And that we don't know what the answer to that is. And so our technique usually for most of the other problems when that happened is we treated that as if it was a whole, and so we would factor something out and cancel it out in order to remove the whole. Well, in this problem, the x is inside the sine. It's sine of 2x. You're not allowed to factor something out of the inside of that. So that technique didn't work, so we were just completely stuck and had to look at a graph on the calculator. Well, this famous French mathematician L'Hopital found a solution to that issue. Maybe it'd be fun to take a look at what L'Hopital looked like. Let's see if I think I have a picture of him somewhere. Here's from Wikipedia. There he is, L'Hopital, born in 1661, so he's really old school. Okay, here's what his rule says. In this specific case, what we really have is we have a function over another function here, and what the rule says is it applies if when we substitute some sort of constant into both functions, if we get 0, and that's our exact case here, right? We had 0 over 0. And if both of those upper and lower functions are differentiable, then we can transform our problem, really. What this notation says is if we have this original situation when we attempt to sub an a in, if we end up with 0 over 0, then we could instead solve the problem and get exactly the same answer by doing a different limit, and this limit would still be as x approaches a, but this says we can just take the derivative of the upper function and separately do the derivative of the lower function and attempt to find the limit again. Looks confusing when we first look at it, but you're going to see here when we do our first example that it really is pretty straightforward. So here's what I'd like to do in the future. Our first example is that first one that I said back in Chapter 2 we weren't able to complete without a calculator. What we should do is we should first attempt the problem using our technique from Chapter 2, which really was to just sub in values. And so I'm going to do that underneath without an equal sign, just because I don't want to put equal signs. I know ahead of time I'm going to get 0 over 0, and this doesn't really equal 0 over 0, so I wouldn't want to say that. So I would attempt to do, let's see, I'd end up with sine of 0 over 0, which is 0 over 0. So that doesn't help me, but it does fit the definition of L'Hopital's rule, which tells me that I can just transform this into another problem. That other problem would be still the limit as x approaches 0, but it says I can separately take the derivative of the top. Well, the derivative of sine is cosine 2x. Don't forget the chain rule. We'd have to multiply by the derivative of 2x, which is 2, all over. This formula says to take the derivative of the bottom thing. The derivative of x is a 1. Well, this time I know I'm not going to get 0 over 0 because I have a 1 on the bottom, so I'm going to go ahead and use an equal sign here and do the substitution. So we do 2 cosine of 2 times 0 in our parentheses, all over 1. How much is cosine of 0? Well, that's 1. 2 times 1 is 2, divided by 1 is an answer of 2. Okay, so an extremely powerful, but it really wasn't all that complicated to pull off, way of any time if we end up with a 0 over 0, when we sub in trying to find a limit, we can apply L'Hopital's rule and just do derivative, and then try to recalculate again. I didn't mention it at first, but what that's called, if you have what that's called in math, if you have a 0 over 0, since we can't determine what that really is, it's referred to as an indeterminate form. There is another indeterminate form, something else that we've run into from time to time this year, and that's if you ever have infinity over infinity. We don't really know how much that is numerically. And good news for us, L'Hopital's rule also works for an infinity over an infinity. So let's try one out where we're going to run into that. So our second example is the limit as x approaches infinity of 5x squared plus 3 over 2x squared plus x. And we used funny math. We didn't really use what I would call solid math in order to solve this back in chapter 2. So what we should do is we should start by trying to substitute an infinity in. I can't really do that. You can't sub in infinity, so I'm not going to use equal signs. But if I sub in an infinity and square it here, I think you guys would agree that our top is going to approach infinity. If I have an infinity squared here times 2 plus another infinity, that bottom's going to approach infinity. So that matches this. It's an indeterminate form, infinity over infinity. L'Hopital's rule tells us instead we can apply the limit as x approaches infinity of the derivatives of these things. Derivative of 5x squared is 10x. Derivative of 3 is 0. On the bottom, derivative of 2x squared is 4x. Derivative of plus x is a plus 1. Attempt to substitute in again. I'm not sure whether I'm going to get an answer, so I'm going to use the arrow again and do some math below. What do you think about 10 times infinity? Yeah, that's infinity. 4 times infinity, and then if you add 1, is still approaching infinity. Uh-oh. We ended up with the indeterminate form again, infinity over infinity. What do you think we should do? Yeah, I agree, we should probably just give up. Nah, we never want to give up. We can just apply L'Hopital's rule again, because we still just have a limit here where we ended up with the indeterminate form. So we'll just apply it again. Limit as x approaches infinity. Derivative of 10x. 10. Derivative of 4x plus 1 is just a 4. There's not actually anything to substitute into this time, so our answer is just 10 over 4, which is 5/2. Alright, so that's two examples, both if you run into 0 over 0 or infinity over infinity. Please be careful, don't always just start using L'Hopital's. You really should only apply L'Hopital's if you do substitute and get the 0 over 0 or infinity, one of those two indeterminate forms. Alright, that's basically it. The only other thing I wanted to acknowledge is, since I brought up the vocab of indeterminate form for the first time, we're not really going to run into these, but I just wanted you to know that these other examples at the bottom of the screen here are other examples of indeterminate forms, so we don't really know what happens if we do infinity times 0, or 0 to the 0, or infinity to the 0 power, or if we subtract two infinities, or do 1 to the infinity. Again, we're not going to run into them, but I just wanted you to be aware that those are also considered indeterminate forms. Alright, that's it. Hope you enjoyed the video. Hope you enjoy using L'Hopital's rule. If you're interested in more about him, go back to that Wikipedia page. You can find it pretty quickly. Alright, I'm out of here. Take care, you guys. See you soon.